Hello everyone. In today's video, we will be talking on embedded C basics. It's not that I'll be teaching about embedded C, but to make the learner understand how it is easy to develop a C programming and how you can easily program on an embedded system or an embedded device, and what is the supporting software which I'll be demonstrating in few minutes, which I'll be using, and even the learners can also use this for developing the code for even a tiny MCU to a higher end embedded systems. So in today's video, we'll be covering about the MDK software, which I'll be jumping in few minutes, and I'll be talking on how the GPIO can be programmed by explaining the features of the software. Hello embedded learners, I'm Geeta. I work as a technical director for ARM software tools at GSAS MSPL. So now let's dive into the MDK software, which I would be explaining on what the software is and how it will be beneficial for an embedded learner to develop the C programming for a tiny embedded system to higher end embedded system. Now let's get into the software. I'm talking about the MDK software today. So MDK stands for Microcontroller Development Kit. Basically, it's a comprehensive or a combined software which is specifically used for doing the embedded C programming for Cortex-M based microcontrollers. And the software can be used to develop even a simple sensor-rated application to the higher end application. And as I said, MDK stands for Microcontroller Development Kit. It's a flagship product from ARM. And what all it includes? It includes compiler, it includes simulation cum debugger, it includes lot of advanced features which I'll be discussing in this video. Okay, so when you install the software, you will be getting this icon, µVision. So just double click and that should open your software. And if you want to download this software is freely available for download from keil.com, www.keil.com, and from there, if you go to products and downloads, you can easily download this software. Or even if you Google Keil MDK software download, you will get this link to Keil site from where you can download this software. So I'm pretty sure some of you, those who have come with the engineering background, or you might have come across this Keil MDK software. Basically, this is the workspace, we call it as, because we work on this IDE, so it's called workspace, and the workspace is called as µVision. So in this IDE, when you open the MDK, you will be getting project window. This is your editor window, which is a smart editor, which I'll be showing in this video. And this is a build output. Build output is specifically whenever you develop your C program, you have written your C program, you have written an assembly program. When you compile it or when you assemble it, I'll just come in few minutes what's the compilation and assembly, though it may be a known terminology to some of them, but I would like to reiterate here because this video is for basic learners, so I would like to reiterate that point. If there is any errors, you'll be able to see it in the build output. So we'll be slowly coming about, we'll be touching on all the specific features of this MDK as I proceed with the demo. Let's start with creation of a project. So to create a project, go from the project menu, click new µVision project. I always recommend to create a separate folder for each project because the IDE, which lot of the other components like compiler, assembler, whatever I'll be talking in few minutes, are part of this workspace, and it generates some intermediate, a lot of interdependent files. So better to create a separate folder and then create a project. Like I've already created the folder, I can create once again. Say suppose test 1. And then I'll give the name of the project, say test. So as soon as I give the name of the project, this is the window which pops up. So this window is basically to select which device you want to develop. MDK supports more than 10,000 microcontroller units. Just select the device what you want to plan to develop, and then you are good to go with the development of the code. So here I'll select For example, because my video series I'm running with LPC1768, which is a Cortex-M3 based microcontroller from NXP. If you know the part number directly, you can type it here, LPC1768, and here you get it. As soon as you select, it will show you the brief description or an overall description of that particular microcontroller. So I'll just quickly go through this description for the benefit of viewers. So this is ARM 32-bit Cortex-M3 microcontroller with MPU. MPU is memory protection unit, and the operating frequency of the CPU is 100 MHz, and this has 512 KB on-chip flash, and it has RAM of 64 KB. So this device can be programmed through in-system programming, IAP. Probably this could be a bit looks like advanced, because these words in-system programming, IAP, these are all the ways we can program the flash of this device. So because this is an ARM based microcontroller, we have various ways to program it, either through debug port or through ISP or IAP. Probably if more information on this, probably you can refer to the datasheet, or even if you find out on Google what is ISP and IAP, you can get a brief idea of what it is. Basically, in-system programming is without removing the MCU or the device from the socket of the board. You can program through it through the serial port or the UART port of the microcontroller, and you can program the flash. In application programming is something, the application will call some APIs or functions which are given by NXP in their flash, some factory default programmed code that in turn will program the flash. Well, so this also has nested vector interrupt controller. So this is just to handle the handle the nested interrupts or exceptions in your application. It has a DMA, it has Ethernet. Ethernet is basically for networking application. And we have USB, we have CAN, we have I2C serial interfaces, SPI, ADC, GPIO, PWM, real-time clock, everything, watchdog timer. So these are the peripherals of this 1768. So just for the quick update, all these peripherals and real-time how to program, how to develop the program, and real-time demonstration of the board, I'll be doing it in the next video. Please stay tuned for it. And now just if I click OK, the ID itself will prompt me to add the startup. So what is the startup code? Probably I'll not go in depth of the startup code, but I'll just quickly tell why the ID prompts us to add this startup code. This startup code is added as part of the source group. So what does this startup code do? Startup code is something the processor executes before it comes to the main function, because when we write C program, it's obviously a program starts with the main function. So before the processor comes to main function, so what the processor has to execute? Basically, when you give power to the board, when you recycle the power to the board, or you give power on reset, the first part of the code which the processor will be executing is this startup. So to quickly tell in few words what is the startup code, it's basically it initializes the interrupt vector table and exceptions for the application, because this interrupt is a very crucial part in an embedded programming. If at all you are developing a code for some peripherals which is generating an interrupt, like suppose you are writing program for ADC, you are given analog input, and once the ADC converts it to digital output, so you, instead of keep polling whether the digital data is being generated, you can give this work to interrupt. As soon as ADC performs its task, it will generate an ADC interrupt, and from that ADC interrupt will interrupt the normal flow of the processor, and processor will understand, yes, there is an ADC interrupt. How will the processor know where it has to go? Because ADC interrupt, I am defining the interrupt handler where I'll tell, okay, this is digital data generated and I want to read the digital data and do further processing, display it or use it for a delay for some application. It is based on the requirement of my embedded system. So through this startup code, we define the vector table telling the processor if some interrupt happens, if some exceptions happen, where it has to go, look for, with specific address in the flash where it has to service this. It's like interrupt Probably I'll be touching about interrupt in the next video again. I have done a detailed video on how the exceptions or interrupts can be handled on the same device LPC1768. So please refer to the video here on this link for more information. So basically interrupt is, it will be interrupting the normal flow of the processor. Processor is going in a flow, whatever the flow what you have written the program, C or assembly. Once an interrupt is generated, it's an alert to the processor. Yes, there is some event happened and it needs attention. So processor has to immediately go there. So for that, it needs the vector table. So that vector table is designed or defined here in this startup code. Okay, I'll come to depth of the startup code probably in the next video. So now let's go to the next part of this. So having added this startup code, next for the Cortex-M, I have to add is system initialization file. So what is system initialization file? And one thing to note in the startup code is it's in assembly code. .s stands for assembly. In this startup code, the main thing which you can configure is stack and heap. Stack, everyone knows, it's a crucial memory required basically to store the variables. Main thing is to store the return address when the processor enters the interrupts or exceptions. And if your application is complex enough where you have written nested interrupts, hope you know the meaning of nested interrupts, interrupt inside an interrupt, then the stack memory size is very crucial here. So we have to be very careful when specifying the size and usage of the stack. So what is this heap? I believe many would be aware of this heap memory. Heap memory is again, it will be a part of the RAM only. But usually heap is used where developers tend to use some dynamic memory allocation functions like malloc, calloc or RTOS application. Why do you need dynamic memory allocation? So you have defined some memory for stack and some RAM is used to store your variables, some data, information and everything. So in your application, if you need a requirement of runtime memory during the application execution, if the processor needs some few bytes of memory for some data storing or processing, it can use heap. It can take the memory from heap. So if you are planning to use any such dynamic memory allocation routines in your program, then please define this heap. So now we spoke about this .s. Now we have to talk about .c. What is the system initialization file? So why it is required? Crucial. So, well, these two files may not be compulsorily required for all the devices. Again, it comes to what device you have selected for your embedded system and which specific Cortex-M MC you are planning to program. But if you are planning for Cortex-M, be it can be lower end Cortex-M0 to the higher end M55, M85, these two files, startup code which is .s and the system initialization files, both are mandatory. Well, now ID prompted me for startup code. Now, how do I get the system initialization file? For that, double click this source group and go to file v5, the folder where you have installed ARM. Go to ARM, go to startup, and here I have selected NXP device, so I'll go for NXP. So as I spoke in the beginning of this video, MDK supports more than 10,000 MCUs. So in NXP again you have various versions, derivatives supported. So I'll go for LPC1768XX, which is because I have selected LPC1768. Just single click, it will add because I have set my mouse setting for single click. Probably you may have to double click. Then it adds. So what is the system initialization file? Why it is crucial and mandatory to add it to the project? Let's come to that. System initialization file is basically, it initializes the clock and memory for your peripherals. So I have touched based upon what is peripherals, what are its various functionalities, different types of peripherals in my previous video. Please watch out here. Basically, as I said, this is for clock. Why ARM stresses on the clock? So what ARM believes is, if the peripherals operate at the same frequency of the CPU, then the overall power consumption of your application is going to be high. When you load this code to the embedded system or the board which you have developed, overall power consumption will be more. So why? For that, ARM has given, especially in this device, LPC1768, there is an option we can specify the peripherals to operate at the same frequency of the CPU, 1/4 of it, half of it, and 1/8. And we are not programming all the peripherals in my application, right? Suppose I want to drive a motor, then I'll only use the PWM. I'll configure the timer as a PWM because this 1768 device already has a PWM unit. I'll configure that. I don't need any other peripherals. So there is also option for this device 1768 where individually it can enable this peripherals. So how do you do that? Though the peripherals are already available in the microcontroller, they have given individual bits in the power control register where I can specifically individually power each peripherals. So based on my requirement, I'll power those peripherals and I'm good to go. And depending on what peripheral you have selected, decide whether that particular peripheral has to execute at the high speed. Like suppose if it's an ADC or something, it has to collect the data, analog data at a very higher speed, then you can set it to operate at a CPU clock frequency. But no, it may not be at the same speed, but it can be a reduced speed. Then you can specify like these options. And that will ensure that the power consumption is less. And whenever you specify this peripheral clock to be CPU clock, it's the same frequency of the CPU. Like this device operates at 100 megahertz, the peripheral also will operate at 100 megahertz. So that is how this system initialization file works, and this is in .c. Well, so these two files are required for Cortex-M. But suppose if you select some other device like ARM7 or ARM9 device, you may not require this system initialization file. But startup code is mandatory, as I said, for giving the interpreter table for interrupts and exceptions. Well, so now this is just I have covered on how to create a new project. I'll just quickly show you on how we can add a C file, though I'll be taking a different project to explain the features of this IDE. So for that, if you go to File, New, okay, so you can save this first. Save for, say, test1.c. Okay, now I will add this test.1.c to the project, because until the files which whatever I've defined or developed, it will not be compiled or it will not be considered until I add that file to this project window. So for that, I'll just double click the source group and I have to go to the path where I have created my project. So and test1. So test1.c. Well, now that I have added the C file, so now let's start the programming. How do you do the programming? In general, what is embedded programming? So everyone tell embedded program is writing in C or C++ and configuring the CU and all. But as per me, embedded programming is nothing but programming of the peripherals. It's correct, right? Suppose, yeah, if I want to drive a motor, then I'll be using the PWM unit. Suppose I want to drive some LEDs, then I'll be using, or a buzzer or something, then I'll be using GPIO. To use the GPIO peripheral also, I need to program the peripheral, configure the peripheral. So how it can be done? I have discussed in the previous video, it is through registers. Registers are nothing but each peripheral has a set of registers associated which the developers can use to develop the code. So suppose I have selected 1768. So I don't know which specific header file has that option. So what is a header file? So this header file will have all the registers definition which are required to be accessed by the user while developing the code for programming the peripherals. So if I give right click, it will only tell me include lpc17xx.h. So IDE is smart enough here and the editor is also smart enough. So I'll tell you why IDE is smart enough and I proceed in this video. Even the editor is smart enough. So as soon as you select the device, create a C file and add it to the project, it will only tell you the specifics. So I'll just open this header file and show you what it is. Because this is LPC1768 and each peripheral has been allotted 16 KB memory, basically to store all the registers which is required to program the specific peripherals. So suppose this is all for IRQ. This is all interrupt numbers, like the system control register structure. There is a system control block in Cortex-M3 or M basically. There are some of the registers, and this is all configuration for GPIO, like whether you want to use a GPIO as input or output, like that. So we have the registers for all the peripherals. Like you can go for timer, you can go for UART, you can go for SPI, can be anything. This is for I2C, this is for SSP, this is for I2C, this is for I2S. There's a sound communication between two devices. Basically, LPC1168 you can consider as an SoC. It has all the peripherals you require. You can use this for developing even a smaller end application to the higher end application. And you have watchdog timer, you have ADC, DAC, PWM. So all the peripherals. So basically whatever peripherals I require to develop my code, to program it, I use it. I can access those registers directly in my C program and I'm done. I can write those program. Yeah, probably you have to refer to the datasheet of this 1768 device to understand what these registers are. Like you want to configure GPIO, you want to configure ADC, what is the status register, how do you configure the status register, how do you enable the specific peripheral, like because it's a 12-bit ADC, how do you enable the resolution. So all those we can be configured through registers. That's the beauty of Cortex-M. And for that, probably you have to refer to the 1768 user manual. If you can go to the NXP site, probably you'll get it, or Google it, you'll get it. Well, so this is about creating a project, adding the C file, and I'll just get a dummy program just to show you how it shows the dependencies. So now what I did was a translate. What does this translate mean? I just said I'll demystify the words: compiler, assembler, linker. These are all the tools which are working in background of this IDE. It's microcontroller development kit. Usually we get carried away saying that it's a hardware. No, kit is a bundle of software components, and those software components of compiler, assembler, linker, simulator, and debugger, which we'll be talking about in this video. So what does this compiler mean? So compiler or an interpreter or a translator, synonyms. Whatever the C program you have written, it will convert that to object code or to the one machine codes. I did talk about machine codes, opcodes, mnemonics in my previous video. Please refer that. In microcontroller, the world in which the microcontroller operates is a digital world. It's just zeros and ones. So microprocessors only understand zeros and ones, which is binary. So if I write, like I'm defining int I is equal to 100, processor will never understand that. It only understands zeros and ones. So this is the functionality. So this is the job of compiler to convert that C statement to the mnemonics so that the processor can understand. Suppose if I give int I comma I is equal to 100. So how it does? Probably if it is, or even if you take any embedded processor programming, if you have done in 8085, 8086 or 8051, how do we do it? First we'll load the register with some value. Suppose I'll just give mu a comma 100. Suppose if I take example of 8051. Suppose if I take the example of ARM, I'll give mu r0 comma 100. So for mu r0 comma 100, there is an opcode associated by it, which has been, that opcode has been associated by LPC1168, that is NXP device. So processor understand that opcode, and then you understand that okay, this particular opcode is like moving some data to the register. So that opcode generation is done by this compiler. Even if I write assembly program mu a comma 100 or r0 comma 100, processor will not understand because it needs opcodes. Again, assembler will convert that assembly language to mnemonics or opcodes. So this is what compiler or assembler does. Any high level language, because ARM, you may think assembly language is a low-level language. True, but it's still the instructions or mnemonics are not understood by the processor. It only understands opcodes. So the job of compiler, assembler, or a translator or an interpreter is to convert your high-level language to the opcode. files. Well, so now as soon as I translate, it shows me these are all the header files. Oh, you metal. Oh, this I have just included header file LPC17XX. How come so many files have come? This is because the MDK software, which is specifically for Cortex-M, what I'm writing the program is M3. These are all the header files which defaults come as LPC17XX. This is your device specific header file. Core_CM3. This is basically to access the core functionality of your Cortex-M3 processor. What are those core functionalities? M3 processor, if you go through the architecture datasheet, we have NVIC, Nested Vector Interrupt Controller, for performing the exceptions and interrupts. And then we have watchdog timer, if NXP has designed it. We have memory protection unit. We have sysdig timer, which is dedicated timer in a core. Whenever user wants, he can use it instead of even timer peripheral. Instead of dedicating a timer peripheral separately, you can use the timer, sysdig timer, which is part of this M3 core. So this particular header file, if I have to open, I'll quickly show you. So some of the core functionalities of your processor, the blocks which are part of the ARM processor. So when I tell peripherals and blocks of the core, they both are different. Because in Cortex-M, the terminologies are different. Inside the Cortex-M3 core itself, there are some set of peripherals which ARM has designed already in their IP. So these semiconductor vendors like NXP, ST, or Texas Instruments, or Microchip, Samsung, even if you take our Snapdragon, Qualcomm, any higher end semiconductor vendors or lower end, they buy this IP core from ARM and they'll put their own set of peripherals. So peripherals can be timers, I2C, SPI, UART, Ethernet, it can be anything. DMA, PWM unit. So they put those peripherals onto this core and they'll develop a microcontroller, and that is what they'll release to the market. And those devices are supported by MDK. And any embedded learner or embedded enthusiast who wants to develop a projects on embedded can select any one MCU and start developing the program. Well, and core CM functions are basically to access the core peripheral functionalities. There are some functions like get PSP for enabling the interrupts, disable the interrupts, all those. This is all interrupts specific to the NVIC, the block which is part of the M3 core. What is core CM instruction function? So there are some instructions which you can directly include in the C program. Suppose I want a delay in my program. So NOP, if you refer to the datasheet, it will tell you what is the delay that particular instruction will give you in your program. So you can include that number of NOPs. So to include NOP in my program, I can directly use NOP in my C program. Or there are some assembly instructions like I want to read the stack pointer, current stack pointer details, what is its, where it is pointing, what is its size, everything. So there are dedicated instructions for it. Those you can still use it in the C program. So core CM instruction is specifically some of the assembly instructions like NOP, WFI, wait for the interrupt, DSB, DMB, ISB, these are all memory barrier instructions. These are some of the load store instructions. So whichever you require in your program, you can easily use it. Okay. Wait for interrupt, wait for event. So wait for interrupt is very useful whenever you want the processor to enter the sleep mode, because Cortex-M3 supports sleep modes. Sleep mode, the processor enters the sleep, but some of the peripherals will still be functioning. In that case, the only way to wake up the processor is through interrupt. So wait for interrupt is whenever you want the processor to enter the sleep mode, or whenever you want to generate a software interrupt. It's not through from peripherals, not from externally, any external interrupts or something. Just in a software, whenever I want an interrupt, I can use this WFI. So like that, some instructions you can use in your C program. So now that we have covered on creating a project and adding C files, mandatory files like startup code, system initialization. So now I'll take one sample project and explain you how we can develop the program and how we can test it in simulator. So because I did tell that in the previous video, here I'll be discussing about how you can write an assembly program in MDK, because it's a very crucial requirement, because in an assembly program, as I already highlighted in the previous video, you have a good control on the processor. you can make the processor the way you want to execute. You can have a control grip on the processor. So for that, you have to write an assembly program. That is the best, because C program, when we write, it's fine, because many users tend to write in C program thinking it's a high level language, and C is very popular in the market, though it is embedded C or a normal C. So everyone tend to write the program in C, but they never understand the C program is just a high level language that has to be again converted to the low level opcodes, which will be done by the tools. But we don't know. Whatever the compiler you're using may add additional code to it. Your code size is going to increase for sure when you're writing code in C. But you're writing in assembly, you're writing the only defined assembly instructions, so that the code size is also reduced overall. So if you want to develop the best optimized code and the code which occupies less space, then the execution of the code will also be faster, then I would prefer assembly. Even higher end, like we talk about Samsung is it's a smartphone device. They also have this multimedia applications where they develop the smart TVs. Sony they were also in this smartphones. These companies still tend to write the program in assembly. They never write code in C. And think, this is only 32-bit processor for Cortex-M. They write assembly for 64-bit processor. So that's the power of assembly program, which many learners just ignore, neglect without understanding the advantage of assembly. Learning assembly is very crucial, even if when you are developing the code in C, sometimes your code doesn't execute, and when you're trying to check out why the code is not executing, that time, depending on this IDE software what you're using, like if your program is using some library functions and you don't have the definition of those libraries, then you can still see that in the form of, because library is nothing but the set of object codes. You can see all those in opcodes. So there again, you need to understand the assembly to understand why this library function is not working, to further debug and understand, troubleshoot why my processor is not executing this library function. So learning the assembly language is the key for doing or to become a good embedded programmer, I can tell. Right. Let's now take up a sample project which I've written in C to show you. Basically, I will be showing only the GPIO part on how we can develop the GPIO, program the GPIO for driving the LEDs here, and I'll be showing that code execution in simulation. Again, this project is for 1768. Here you can see again the same files, startup, system initialization file. So the board is basically the one you can see it behind, which is MCB 1760 board from Keil that has a graphic LCD display. So this particular file is for that, and serial is for UART. LED is what I'll be interested. And this actually also has an ADC, but ADC part I'll not be touching, because in my next video series I'll be talking about the ADC theoretically and how it can be programmed practically and show you hands-on on the board. Right. So now so this is my Blinky C file. Here all this LED initialization, serial initialization, ADC we are not doing. We are only concerned about LED initialization. But I'm not modifying the program, I'm leaving it as it is. And then you can see this blinking of the LEDs in this LED off, LED on, LED out. These are all the functions. This is initialization of LED. So where we'll be telling the LEDs on the board are connected to which, it's been driven by which port lines, with specific port bits. In this case, it is merge of port 1 and port 2. LPC1768 has 4 ports, port 0, port 1, port 2, port 3. In that, the LEDs on the 1760 board is driven by port 1 and port 2. So both you can see here. Some bits are port 1, some bits are port 2. So here I'm specifying it as output using the FIO direction, as a name suggests. DIR is a direction register. FIO stands for fast input output. LPC1768 beauty is the GPIO blocks in the device can be operated at the same frequency of the CPU. If it is operating at the same frequency of the CPU, it will become as fast GPIO. If it is like reduced frequency, then it is slow GPIO or a normal GPIO. So in this program, it's fast GPIO, FIO. This is fast input output direct. Well, and then we have LED on, LED off for making the LEDs go on and off. Basically, it's shifting, like rotating pattern or shifting pattern you can see in the LEDs. Okay. So in this project, I want to quickly explain options for target. So basically, I spoke about µVision workspace. I spoke about the components which are part of this. So, but I didn't tell about how these components can be configured, right? Like we have to sometimes configure those components in our project as per our requirement. So for that, what we do is options for target. You can get the same thing from the magic stick if you click here. So this is the options for target. The first tab shows device. Quickly, I'll be covering this. Probably this I'll be getting into depth in the next video, where I'll be talking in programming part and real-time demo. So quickly, the target tab is basically to specify the memory location. So as I said, the ID is smart enough. Whenever you select the device, it selects whatever the available flash size, its starting address is 0, and size, which is 512 KB. Then RAM. So this particular 176 has RAM divided into 2 blocks. One is starting with 1 followed by 7 zeros, another followed by 2 followed by 7 zeros. So you may ask why these 2 RAMs are required. 176 device, as I said, it has lot of peripherals, including lower end to higher end peripherals. Higher end peripherals like Ethernet and USB. So this specific RAM, if required, you can use it for any other application, but these memories are dedicated for USB and Ethernet peripherals only. So if at all you're planning to use Ethernet and USB, then you can go for iRAM 2. But if you want to just writing a simple program and you still need the RAM, because stack also goes to that, and the peripherals, basically your variables, whatever you define in your program, all those go there. Well, then anything off chip is other than the on-chip memory. If your requirement is more than 512 KB flash, means if you expect the code is bigger enough and it has to include a lot of other functionalities where the size of the code is expected to be more, then you can specify anything. You can interface external memory to this 176 site and you can still expand its memory. By the way, Cortex-M has a memory map of 4 GB. I'll not go into depth of it, but you can interface external flash or external RAM depending on your requirement. Output is like it generates the final output file. If you want, you can create a hex file if you want to program it through ISP or IAP, or if you want, you can generate a generate a library file. You can use this as a library file as a reference for other projects. Then listing, compiler, assembler, linker has its own listing file, but the map file generated by the linker will give you a lot of information. So I spoke about assembler and compiler. I did not talk about the linker. Linker is basically, it takes the files generated by the compiler, assembler, and in your program, if you have used any library APIs or some functions from the libraries, so linker will take that reference as well. And as the name suggests, link, it links all the required files, and links compiles it again. Compiles means it builds the project. What do you mean by building? Because if there are some cross references, because one function is called from another file like that, or assembly program is calling some other function from C file, so all those cross references, even if it is in the functions or variables, everything, it will try to build, it will resolve those, and it will generate one single file, which you can test it in the Keil IDE. We call it a simulator, which I'll come to that. Or if you have a device already ready, hardware ready, you can download the code to that board and you can test it. More on this downloading part I'll complete in the next video. So C or C++, MDK software allows you to write the program in C or C++. It is an optimizing compiler. Means based on how you are writing your C constructs, how you are writing your C program, compiler will try to reduce your code size. you have different levels of optimization. Okay, and ASM linker. So as I said, linker, it will build all your entire application, your codes, and it also locates your code. What does it mean by locate? Now, because I know the flash of this 176 starts at 0 address and RAM starts at this address. When I'm writing code in the IDE, when I'm testing it on the IDE where there is no hardware or embedded system connected, it may still work because there is no hardware. Virtually I'm testing it. But if you want the same code to work on the hardware, then we have to clearly tell, actually in my hardware board, where is my flash starting address, where it is sitting, what is its size, starting address, and RAM starting address and size. If you specify that correctly, then only linker will be able to locate all your code part, program part in flash memory, all your data part, variables, stack, everything in the data memory. If you don't specify that address correctly, then you cannot expect this code to work on your device at all. This is called as retargeting. We have to clearly specify the memory because memory is very crucial, because linker is the one which locates your code to the flash and data to the memory. So you have given here use memory layout from target dialog because it takes from target tab. Well, so debug, here you can test your code in simulator. Simulator is a virtual target, means without connecting any hardware, I can still test my program in the Keil IDE itself. And I can check out how it actually performs on my processor as well without connecting the processor. Second option is, if you have already hardware ready, I can use that hardware and you cannot talk we cannot make the MDK software to directly talk to the hardware. You need a medium. So that medium can be sometimes external debugger hardware, or it can be a firmware which is already programmed in the hardware. So probably I'll come to this in the next video when I talk about real-time demo. Right. So now we'll just build this project. Build is here. You can access the same thing from here. Project build. You also have something called as project rebuild. So rebuild is when you want to build all the C files or assembly files which are part of this project window. Build is, suppose because here it's only 5 or 6 files, but when it comes to real-time programming, you may have more than 20, 25 files or even 50 files. In that only you modify 2 or 3 files. So to reduce the overall build time, there is an option called as build. So what the IDE will do is, whatever the files which are modified, it takes that modified OBJ files, because compiler generate object files, and then it takes the same previous copy of the OBJ files for the other files, so that it need not again compile and generate the OBJ. So that's the difference between build and rebuild. Now to enter the simulator, you have to click from debug, start a stop debug session, or you can directly click this D button. So I'll go from here. Sorry. So this GPIO block, I'll just close this. I'll just show you from where I open this. So you can access this from peripherals, core peripherals. You have to go to GPIO, fast interface. So you have 5 ports here. I'm using port 1. Okay, so now I'll just run the program. Detailed explanation I'll be giving in the next video. I'll just run the program and you should be able to see this pins changing. Okay, so because this is in the simulation, suppose maybe you're not able to see that bits. You can see here one by one, this bit was clear, now this bit is set, again this bit is set. So that is how it works. Here it is only GPIO 1 I have opened because as I said, this LEDs on this board is being driven by port 1 and port 2. I can show you port 2 as well. So this is the testing of GPIO on 1768 MCU in simulation part. I have not connected any hardware, so you can check out, it's a simulation here. Well, so now that we have seen this in C program, let's do the same GPIO programming in assembly program. So as highlighted in the previous video here, that I'll be touching about today on how to create an assembly program in Keil. I'm pretty sure you may not get this video anywhere. So I just wanted to touch on that topic on how we can create an assembly program. Though I explained this program in the previous video, but today's in this video I'll be telling how you can write the assembly program, what changes you have to do in the project so that you can write your program in assembly and processor executes it's fine. So for that we will go to, so I'll be taking the same project which I took in the previous video. So for the explanation of this, please refer to the previous video where I had explained this program. What are these registers? When I spoke about how to do the GPIO programming. The main intention of bringing this project again here, because I said there in the previous video that I'll be covering how the assembly programs can be written in Keil. So for that, you have to modify the startup code, which is very important. So in Cortex-M3, reset itself is a high priority exception. Probably I spoke about this in my video on exceptions, interrupts in depth. So please refer to that for more information. So reset, as you everyone know, processor has a reset, and in Cortex-M it's a exception itself, high priority, which the processor has to service it. Without that, it cannot go further at all. So once a processor comes out of the reset, how it can be through when you press the reset button on the board, or you are recycling the power to the board. So in this reset handler, which is an exception handler, in this I'll be modifying. Here it is, reset handler is the system initialization for initializing the memory and clock for the peripherals. Then I'm giving something called as import GPIO. So what is import? As the name suggests, import means I'm importing this from some other file. So what is this GPIO where I have defined? I have defined it in here in the GPIO file. So you can see it's a .s file. It's an assembly instruction file. You are writing program in assembly. Export GPIO here I'm giving. Why I'm giving export GPIO? Because this GPIO is referenced in startup code. So that's the reason I'm giving here export, and in the startup code I'm giving import. Okay. So here I'm giving import GPIO. Then next, what is that I'm changing? First, it has to do the system initialization, because these two are nothing but the functions for me. It's the functions as part of these two files. So I'm giving register R0 to point to system initialization, which does the clock and memory settings for the peripherals of my MCU. Branch BLX, branch, link and exchange. From this startup code, it will go to system initialization, which is C file, execute, and it will come back. It will link back to this instruction. Then I'm pointing R0 to GPIO. So GPIO is this part. This is my actual program starts from here. So after that, then I'm giving branch X R0. So what it does is, it will jump to the GPIO. So the main thing when you're writing programming assembly for MDK is you have to modify this startup code so that your code executes. Well, even without startup code, you can write assembly program and you can still check your program in simulator. It works. But if you want this assembly program to work on your hardware, these two files are mandatory. You cannot skip these two files. Okay, so now if I come to GPIO, from here it goes to branch X R0. So R0 is pointing to GPIO. It comes here. So here here I'm doing all the direction register for specifying it as input output. Then to to turn off some specific LED, I have to write the specific bit in the clear register. To set the specific LED, I have to set the specific bit in the set register. Okay, so again I'll enter the simulation, and here you can see it comes from the startup code. So if I do single step here, R0 is now loaded with system init. So system init, this is the address of my system init function 165, which processor will execute. But I want the processor to execute from GPIO. So what I have done, I put a breakpoint. So what is a breakpoint? If the code is lengthier, though this is a small one, but if you have written some 25k lines of code, usually that is not practical. But suppose, let's take example 1000 lines of code, and I want to instead of executing, seeing how the processor is executing every instructions or see, I'll put a breakpoint. Break, word such as break. You are breaking the execution. It's like halting the execution of the processor. It will put a break. When I just single click here, it just shows the red circle. That's the breakpoint. But please be noted, you cannot put breakpoint on this light color. You can see some of the fields here are light color. Those are not executable. There is no executable code present there at all. Only where you see dark gray is the place where you have to put a breakpoint. Suppose if I try to put here also, it doesn't come. It shows like this. There is no code there. So now I'll run, and the processor comes here. It's now GPIO part. Then you can do single step, and you can see how the registers are assigned, registers are getting loaded, cleared, set, everything. So to show this on and off of the LEDs, I put a breakpoint. Okay. So please watch. It shows these 3 LEDs set. It's been set. Again, if I run, these LEDs go off. So this I've just taken only 3 bits, but the same program, if I load it to that board, it works because I have added the startup code, system initialization file, as well as the ports. Here I'm just showing port 1. You can extend the same thing for port 2 as well, because some of the LEDs are driven by port 2 as well. So this is what I wanted to cover on how to write an assembly program in Keil, which is a very important, interesting topic. So today we just saw how you can write a C program or an assembly program, and what is the supporting software. We spoke about the Keil MDK software, and we developed a small C program. Like initially, I showed the creation of new project, how to configure the components in your IDE, various software components in the project. Then I showed how we can do the assembly programming. So now the key takeaways for this video, or I would encourage the embedded learners, is you can start up with a small thing like select an M0, STM32M0, which is a lower end microcontroller, which has a less flash size, limited set of peripherals. Start working on it. You can develop a program in taking this MDK software. You can develop the code for STM32. Then if you are going for a higher end application, you can select M7, Cortex-M7 or M4 with a higher end peripherals like USB, Ethernet, or you want this real-time operating system where real-time control is required in your application. So for all those, you can select a higher end device and you can start developing the program based on your requirement. Thanks for your attention, and please stay tuned for my next video. We'll be talking about touch basing on the theoretical part of timers, PWM, ADC UART, and as I will be showing you in practical also how to develop the program and in real time see how these peripherals are in action, how it performs. Thank you. See you soon. Bye-bye.